we're going to start by verifying what we claimed at the end last time. And that is that this impulse train, the Fourier transform of the impulse train, is also an impulse train. Okay, so how can we see that? Well, it's a little bit hard to verify from the Fourier transform integral because on both sides of this transform we have delta functions, right? And the way that we checked Fourier transforms of delta functions was to always integrate the side that had the delta functions on it, but they both do. So you're not going to easily be able to plug this in and check that it's correct. We'll do it in a roundabout way. So we want to verify this. Of course, we have a name for this. It's the we're calling it using the Shaw notation. It's this function because that's what it looks like. It's a delta train. And on this side, we get the same thing, except the scaling is that the width between delta functions is 1 over Ts, or sample frequency. Okay, so we're saying these are a Fourier transform pair. Now, we're going to verify this using the Fourier series instead. That'll give us a way to do this. Okay, so this is the first main thing we need to cover so we can get on with sampling. All right. So first of all, let's let x of t be this this delta impulse train, and let's do a Fourier series to calculate the coefficients. So notice this has period Ts, so it's okay to apply the Fourier series here. And the Fourier series coefficients will be this integral. Now we integrate over one period of our signal. Now, normally we integrate from, let's say, 0 to Ts, but remember, any period is equally good. And if I integrate from 0 to Ts, I'm going to have some problems because the limits of my integral will be exactly where the delta functions are. And we do not like integrating discontinuities times the delta function. So we need to either have the delta function in the interval or out. So it'll help to integrate over this interval, Ts over 2 to Ts over 2. That's also a period of this thing. And now what you'll notice is this has exactly one delta function within that interval, right? Because this signal is simply like this, 0, Ts, 2 Ts. It's just got a bunch of these, right? And the interval we're looking at here is Ts over 2 to negative Ts over 2. That's where we're integrating. So only one of those delta functions is in that interval, all right? So this is going to be equivalent to not summing. Just do the 1 over Ts integral. And just take that one delta function that's in the interval. The k is 0 for that delta function. All right, so within one period, this is a very simple function. It's just a delta function. Well, we can do this integral, and we're going to get that this just equals, well, sifting says that you plug in the value 0, that's where the delta function occurs, as t. So e to the negative I 2 pi k over Ts times 0 for all k. Well, that's just 1. So it's 1 over Ts for all k. Okay. Now, in other words, it's constant. Every coefficient is the same. It's 1 over Ts. All right. So we should already be familiar with this because we knew. I mean, we had done a Fourier transform of a delta function in continuous time, like not a periodic one, but we knew that the Fourier transform of a delta function is what? Delta function of t goes to what function in frequency? So what's the Fourier transform of a delta function? Think of what's the spectrum of this thing. Yes? What? Sine? If it were a shifted delta function, then yes, it would be a complex exponential. This simple delta function that has no time shift is even simpler. It's just 1. Okay? So it's just 1. It has all frequencies equally. All right. So we see that the periodic delta function, which we just did above, is also constant, except for now these are coefficients, not an entire function of f. Okay. So the last step to do what we set out to do here is to say that let's convert this continuous time Fourier series to a continuous time Fourier transform. We had a discussion about that a few weeks ago. We said that Fourier series you can interpret as a Fourier transform by making the coefficients be delta functions. Okay? So in other words, x of f, the Fourier transform of the above signal, is just this. In general, it's always the Fourier series coefficients, delta of f minus k over the sampling frequency, right? Okay, and or the period. I'm sorry, not the same. Yeah, the period of your signal. So that's always true. And now let's plug in our AKs, and they're all constant. So it's just this thing. And that's what we were trying to prove, that the Fourier transform of the impulse train is an impulse train. Okay, so that was very simple. I want to give you one more look at this, just to provide more intuition. Think of it as practice for how to deal with Fourier transforms. So here's a different look at verifying the same relationship. So here I'm going to consider the discrete time signal. And really, all I would need to do was consider the discrete time signal that's a constant 1 everywhere. But I'm going to make this a little more general just for the exercise. Okay, so let's say it's a complex exponential, e to the I2 pi for some frequency f naught n. It's a discrete time complex exponential. If f naught is 0, then this is just the constant 1. And that's really all you need for this intuition I want this to provide. So all you have to do is consider the constant discrete time signal. Okay. Now, notice that, remember that we have a way of interpreting a discrete time signal in continuous time. Okay. So the continuous time representation of, for example, the constant signal it would be x of t. You would use delta functions to represent the values of this discrete time signal. So for the constant, it would just be this delta train. Well, it's always represented with delta functions by the values of the discrete time signal. And in this case, because it's constant, that would just be sum of the deltas. So it's just a impulse train with period 1. Okay, with sampling rate 1. So it's interesting to think the discrete time constant signal is actually sort of like this sampling function. Okay, if you convert it to continuous time. Well, that gives us an easy way to check what we want. We should look at the Fourier transform of this discrete time signal. Now I'm going to go back to the more general case where we're looking at xn being a complex exponential, not necessarily 1. Again, just for the exercise of it. So in continuous time, we knew what the Fourier transform was for complex exponential. Let's write that down. We knew this pair. We verified it before. Okay. And how do we verify that? Well, we always do it the direction away from the delta function. So we verify with the inverse here. Okay, plug that into the inverse Fourier transform, you'd get this relationship. Now, we can do the same. Now we want to get the discrete time relationship. Well, we can do the same technique. Remember, the discrete time inverse Fourier transform. How is it different than the continuous time inverse Fourier transform? What do you think? How is the discrete time inverse Fourier transform different than the continuous time one? Any ideas? So if you look at the formula, there's only one difference. Aside from changing the t to an n, there's only one difference. You integrate over only one period because discrete time Fourier transforms are periodic. Okay? So you only integrate, usually you say 0 to 1 or negative half to half, or something like that. So what that means, though, is that this relationship will still hold. In other words, we know that if we integrate delta f minus f, a delta function at some location f naught, that this should equal just e to the I 2 pi f naught n, okay, as long as that delta function's within the interval. But we can integrate over one period here. And that period, as long as that period contains the delta function, this is going to be true. So what this means is, what we've deduced by this is that we know that the Fourier transform of any discrete time signal is periodic. So by assuming that this has period 1, then we know that xf is the periodic extension of the above. Oh, sorry. So we take the above, and we also do a periodic extension here. Okay. So now, if that's confused you, just draw a graph, and it will become very clear. So what we're saying is, here's 0, here's f naught. What we're saying is that in continuous time, if you have a complex exponential, the frequency domain is just a delta function there, right? Now, in discrete time, it has to be periodic. And all we're claiming is it's the periodic extension of this with period 1. So here is, let's say, let's let this be 1 right here. And this is negative 1, negative 2. Then the Fourier transform is actually has, oops, I don't want to. So it has a delta function at intervals 1. This type of thing. Okay, and usually when you plot or when you want to visualize the Fourier transform of a discrete time signal, you only look at one period. You ignore the rest because you know it's a periodic extension. So here's so maybe you're already getting the hint. This is the relationship here. The intuition I want you to get from the second look is saying, well, we could just consider that the discrete time constant signal is like a sampling function in continuous time. And its Fourier transform is the impulse train in frequency. There we go, a second way to see that this is true. Okay, so now if there aren't any questions about that, we'll go on to applying this to sampling. So here we go. We've assumed that let's assume that you sample a signal, ideally, like we discussed, by taking the continuous time values spaced out with width ts, the sampling period for all n. So now we have our discrete time signal. So what we've noticed already is that this is equivalent to doing a multiplication of your continuous time signal by this sampling function, this impulse train, ts. Okay, so that represents a multiplication, and what comes out, we'll call this the sampled continuous time signal. Okay, so this notation just simply means that x sampled of t equals x of t times this SHA. Okay, that's what we mean here. Now, so why is this sampling? Again, we have a signal. We've got our sampling period. And we have something like that. And when we do this multiplication, we get delta functions that get scaled by the value of the function. And you see that scaling becomes the samples of our signal. There's this green is the output. That's xs of t. It's green. The blue was x of t. Okay. Now notice that there's one thing we do not have in accordance with how we set up the problem. Xn is a discrete time signal. This xn we've defined here, and yet this xs of t is a continuous time signal. But we can easily see that this is the discrete time. Xn is the discrete time equivalent of this xs. So they're equivalent to each other. So let's just deal with the continuous time version. Great. Now to understand what sampling did, we can use the multiplication property of the Fourier transform. So let's look at the Fourier transform of this sampled signal. Well, we know that we just did a multiplication, and the rule for the Fourier transform is multiplication in time is convolution in frequency. So, in fact, this sampled signal in the frequency domain is just x of f convolved with another impulse train, which is the Fourier transform of the first one. We have a 1 over ts there, and this spacing is 1 over ts, which we might call the sample frequency. So this is what happened to our Fourier transform when we sampled it. We did this convolution. So let's suppose that we have a signal that originally the x of f looked like this. All right, so this is our x of f. Now, if you sample it at widths 1/10, so you take a sample every 1/10 of a unit in continuous time. Okay. Question is, what is xs of f? Now, I'm going to give you a minute to think about it, and then I want a volunteer to come up here and draw what the Fourier transform of the sampled signal is. Okay, so essentially you want to perform this convolution. So give you a few moments here, and then I'll ask for a volunteer. All right, who's daring? Who wants to come work it out? I'll give you hints. Work you through it if you have trouble. Someone think they can do this convolution? I think you want to try. Yeah. And there's going to be another, I'm going to give another volunteer a try in a moment. And the second one actually might be a little harder. I'll throw out the second one to you. You can start thinking about it. What if the sampling rate was TS equaled 1 instead of 1/10. Okay. So come on up here. Thank you. So I'll give you some space. This pen, you can just use, you can use colors if you want. You touch the top to pick your color. Don't push that button. Just draw. You can put your hand on the screen. It doesn't matter.
Okay. So our formula for x of f involved with the delta train. Oh god.
Yeah. If you rest your hand, it's easier to write. Most people avoid it because they think their hand will mess it up. But yeah.
Is the integral from negative infinity to infinity x of tau delta train of t, or I guess f minus tau. Okay. So the shifted delta train. This is alright. So let's rewrite what the delta train is. The integral from.
Can I give you a suggestion?
Sure.
When you're in this starting form,
Yeah.
just think of, just go directly without applying the integral.
Okay.
Just use linearity here and say that this is a sum of deltas.
Yeah.
And each delta we've worked out before what the convolution is.
It's x of f convolved with the sum of delta of f minus kts. Okay, and that's equal to the sum of sum of x of f convolved with delta of
Great. Now you just have to know what that convolution is.
Right, so the convolution is going to be the shifted x of f.
Yes.
The sum over k of x of f minus
Great. Great. Now try to draw it because I gave you an x of f here.
okay.
Sorry, we'll use the down arrow. That sometimes works better.
Okay. So draw this.
So yeah, we.
First one.
Yeah, exactly. Oh, the fingers are turned off, so you can use the pen, or you can just use these. Yeah. Yeah, I'll tell you what it was. It just went from -1. It was diagonal.
Okay. To 0.
Yep, and then it was just like square up to 1. Exactly. Yeah, the fingers are off. I know. It takes you a while to get used to it.
All right. Okay. So this would be k equal to 0. K equal to.
Here, let me make one correction. This should have been a 1 over TS here in the frequency. So K over TS. Yeah. Good.
Okay.
Good.
So f minus 10 kts basically. For 10k.
Mm-hmm. Mm-hmm.
Okay. So the next one's going to be way out here. This is so you shift it by 10, so this guy's going to be 9, 10, 11. This.
Great.
So it's just going to be
Perfect.
a train of these
Yep.
separated by a distance v.
Nice. So it just keeps going in both directions, right?
Yeah.
Okay. Perfect. Great. Let's get a round of applause. Awesome. You see what happened here? He worked out by formula what was going to happen. You're going to get a bunch of your original spectrum shifted by the width of the delta function. Because what you had was a convolution of this original one here, right, with the other signal, the sampling function was a delta function here, a delta function here, one at 20, one at -10, and when you convolve with the delta function, you just get another copy shifted. Okay. Now, there's one other thing. It's not a big issue. There was supposed to be a 1 over TS here, so this should have been a 1 over TS on each of these guys, which would mean instead of 1, the new height here would be 1 over TS. But really, conceptually, that's not going to change what we're talking about here. Okay. Does someone want to do this now for sample rate of 1? What if TS, not a sample rate, a sample period of 1. So this is, before that sample frequency was 10, right? If we invert the sample period, the sample frequency of the example he did was 10. Now we want to do a lower sample frequency of 1. Okay, someone come do this exercise again. I need a volunteer. Everything's the same that he did except for the final step of actually summing it up, right? So up to this point, the formula is the same, except for it's not 10 anymore. So you're getting copies shifted, but somebody can be daring. Come on up. Great, thank you. So let's get you some extra space. Okay. Yep. So go ahead and try and like draw this with its shifts and try to add them up or something. Oh, I thought you were pushing that button. Don't worry about it. Yeah.
Okay, so it still go to 1 over 2. Oh.
I get to 1, so yeah, so now it's just 1.
And then here, it would still be at 0.
Yeah.
It would go up and sum with the 1.
Yeah, so I find it helpful just to like draw the original copies and then try summing later, but whatever works for you. Yeah, that's a good way to do it. Nice. Maybe if you draw the third copy, you'll see where it goes from there.
So that one ended.
Yep.
So,
Yep.
is that okay?
Yep. Exactly. So, except you would have a copy backwards too, exactly. Yeah. Perfect. Thank you. So you see, again, the result has to be periodic, okay, with respect to the sample frequency. Here the sample frequency is 1, so this result now is periodic with period 1. And so it's this sawtooth-like spectrum, all right? So notice what made this one harder than the previous one. The shifts overlapped with each other, and you actually had to do a sum. In the previous case, they didn't overlap. Okay? This is actually the key point of sampling and how you make sampling work. Okay? Let me illustrate this example a little bit further. Okay, so here was our original spectrum, 0, 1, -1. Here was what we were trying to convolve with, a delta train. Zero, 1, 2, -1. Okay, and the answer was, and I'll use colors to do exactly what she just did a minute ago. Was this? We had the original. That was our x of f. We had, and now because of the convolution with the deltas, we had shifts. There was our x of f minus 1, and so forth. We have another shift, and these just keep going. All right, let's do one more. We have a shift this way as well. And then these get added together. Okay, and you get that sawtooth. But that's going to be problematic from a viewpoint of sampling. Okay, here's why. Notice that once these things are added to... Okay, well, maybe I should just go on according to plan here. Okay. Let's talk about something called a band-limited signal. So we would say a band-limited signal has the property that the Fourier transform is 0 if the frequency is too high, above some known maximum frequency. So this FM, let's say, is the maximum frequency. Now, in general, when you're sampling, you don't know what signal you're sampling. If you did, why take samples? You know what it is already. You're taking samples of an unknown signal, but you may know that it's band limited. Okay? And if you do, then, so let me draw what this band limited means. Of course, it means that, if you plotted the spectrum here, you have your maximum frequency, and it's just saying that the Fourier transform lives within this band at 0 outside. Okay, so there's an example of a band limited signal. Now I'm drawing Fourier transforms like real valued functions. That's just because for this discussion we only need to know where the spectrum is. Of course, it's complex valued. We know that. Okay, so here's the sampling theorem. And this is referred to, it's the Nyquist sampling theorem. Okay, if the sampling frequency, which is 1 over the sampling period, is greater than twice the highest frequency, then your signal xt is uniquely determined by its samples. So you can recover it completely. Okay, so this, many of you had actually heard of this, because the first day of class, we did something related to sampling, and some people knew that CD audio was sampled at 44 kilohertz, because that's more than twice the audible range of 20 kilohertz. Okay, so many of you have actually heard of this, but did not know the justification for it, why it works. And now, with our understanding of the Fourier transform, it becomes very simple to understand why it works. Okay, the exercise above already showed us why it works. Because there's no overlap caused by aliasing if this property holds. Okay, let's go back to our examples. Notice that in this first case, notice that this signal is band limited, right? What's the highest frequency in our original signal? Let's go up here. What's the highest frequency in XF? It's 1. Okay, so this is band limited. F max is 1. So that means if we sample at a rate higher than 2, we should not lose any information. Now, what does it mean to lose information? In this case, it means if you get overlap, you lose information. Why is that? Well, each copy of the spectrum can be referred to as aliasing. So we've talked about aliasing, how in discrete time the same sinusoid can go under 2 different names or many different names when they're separated. Well, these, the fact that you get repeats here is the aliasing artifact due to the sampling. But the aliasing artifact people usually refer to is only when they overlap. So notice in this case, in the second example, we sampled at a rate too low, right? And we got overlap between this part of the aliased spectrum and this part of the original spectrum. Okay? Now, when they overlap, they get added, and there's no way to just go unadd them. Okay? If all you have is this resulting spectrum, and I say, what was the original signal that it came from, you're not going to be able to separate out the aliased frequencies from the original frequencies. Okay, and that's going to be a problem. So you can't recover. Okay, so as long as there's no overlap, you can recover, even without knowing anything else about the signal except that it was band limited. All right. So that argument is my proof of this theorem. Does everyone believe that? Yeah. Yes, let's talk about anti-aliasing. Because how does anti-aliasing work? I mean, when do you do anti-aliasing with respect to sampling? All right. So I'm glad you brought that up. Let me first say, how do you recover? Then we'll talk about anti-aliasing. So it seems like from an information point of view, you haven't lost information if you satisfy this theorem. But let's just give the scheme for recovering real quick. Okay. How to recover x of t? Well, notice, let's just do this by picture. Okay. You started with a spectrum. I'm going to change it now. I'm going to just use a triangle because it's easy to draw. So you started with this a spectrum like this, let's say. There was this is x of, well, let's say the blue is x of f, the original spectrum. Now you sample at some frequency that's high enough. So let's say twice FM at least. So let's put it up here, Fs. Okay. The result of your sampling, here's the negative Fs, is that you get copies of this at those different locations. So, and you get it scaled. The scaling again is not super important, but let's put it here anyway. So you get that thing, but it's scaled to be a height Fs, and you get copies as well. And it's periodic. Right? So that's x, the sampled spectrum. Now, to recover, all you have to do is apply an ideal low-pass filter. Okay, so let's say here's what filter should we apply? Well, we want to get rid of the extra copies, the aliased ones, right? So we're going to apply a filter that does this. It'll go up to Fs over 2, and that's sure to get rid of all the extra copies. And the height, just to renormalize, let's make the height 1 over Fs. So we'll exactly get back to our blue if we multiply these. Of course, that's what happens when you apply a filter. You multiply. Okay? So you see that this recovers, and voila, in discrete time, in the time domain, what is this filter? It's a convolution. Convolution with what? Sinc of FST, which is exactly what we had called sinc interpolation. So now we see why sinc interpolation works. Assuming your signal is band limited, sinc interpolation is exactly going to recover it. Okay? See how easy that is once we know the Fourier transform? All right. So let's say what happens if you don't obey the theorem. So if the sample rate is too low, and then let's say we do know, just for kicks, let's say we have a spectrum as an example where it's got like, more interesting shape to it. So let's say it's sort of like this and like this. Okay, so there's the original spectrum. And let's say we go sampling it. Here's the highest frequency is up here, but let's say that we do Fs right about there. So clearly not high enough, right? Okay. What's going to happen is you get your copies. I'm not going to worry about the vertical scaling in the picture. And the copies do this type of thing. Okay, now let's say you go back and you do you apply your reconstruction, which was a low-pass filter. Okay, so and that's what you have back. Well, it's clearly not the same as your original signal. Your original was the black. Now you have this new thing. But even more interestingly, you have these weird, this aliasing effect here, this aliasing artifact, which introduce new frequencies that weren't even there potentially. Maybe it just adds to frequencies that were there already, but it could introduce completely new things. Okay, now remember my example in lecture 3. The third lecture, I pulled open the MATLAB for the first time. I started messing with the sound file and doing weird things. And one thing I did was I sampled it at a very low rate and played it back. And you got new sounds that were not there in the original sound. Okay, they seemed totally out of place. And that's because we didn't have this, the signal wasn't band limited and I went at a too low of a sample rate. So that was the aliasing that we were hearing. You can go back and watch the video. It's near the beginning of lecture 3. And so that's exactly like what this picture is showing. Let me show some other examples of aliasing that maybe you're familiar with. If you go to, for example, YouTube and you do car tires spinning on video. So notice what happened here. I'll do that again. So a car is moving. Its tires are obviously spinning. But because of the frame rate of the camera, when you get spinning fast enough, it looks like you're not spinning anymore. That's exactly the aliasing that's going on. When the sinusoid gets too high and it's been sampled, it looks like a low frequency. Okay, so that's exactly what's happening here. See, it looks like it stopped, but it's not. Okay, there are many cool effects. If I had time, maybe I'll post some to Piazza. Some really cool effects people do with this aliasing. It looks really neat. Here's another thing that happens with images. Okay, so this example I gave here was aliasing with respect to time. The individual pixels were not sampled at a fast enough time, right? And so what should have been a very high frequency was coming through as a very low frequency. All right, that's what was happening here. Here's another thing with images where it's aliasing over space. Okay, if you have a screen door, this is like a screen door effect. If you take a photo and it wasn't properly anti-aliased, okay, if it's just capturing pixels, you can get these weird effects, which you've probably seen before. Notice how there's these weird circular shapes in what should be just vertical lines, right? This has to do with how the pixels line up with the screen door or whatever you're looking at. Okay, so this is improperly, you can view this and the previous one as improperly sampled signals. There's a way to avoid aliasing, to get rid of these artifacts. And I want to mention that right now. What do you do if you can't always just increase your sample rate, right? The camera only takes pictures at a certain rate, or you have a certain number of pixels, right? But what you can do is remove the content that you know you won't be able to capture. Actually, it's not the next thing I want to say, but all right, I have a few minutes. Okay. Let me just say some vocab first here. Maybe I'll jump straight to it. Okay, the usual thing you actually do is you do a, so I'm going to say these are practical considerations. And one is that you always put an anti-aliasing filter before taking samples if you sample properly. And the reason I interrogated you about the details of the anti-aliasing filter when you brought it up is because it's crucial you do this before taking the samples. You do a low-pass filter to avoid aliasing. Before sampling. All right, so here's how you would actually build a sampler. You would say, you would do, your continuous time signal comes in, and in continuous time, before you do any samples, you make sure there's no frequency content above what you're going to be able to capture. Okay, if this was audio, you filter out everything above 20 kilohertz because you say, I'm not going to be able to hear it anyway. But if you don't filter it out, it's going to get aliased and cause things you can hear. Okay, so you filter it out. So you do this low-pass filter at fs over 2. Okay, and once that's been done, then you know you're not going to get this weird artifact. So now you sample at a rate of fs. Okay, Good. So if your actual spectrum was originally outside of the range that you could have dealt with, so let's say here's fs over 2, and here's negative fs over 2, and suppose you had something that actually had some content outside there. Okay? What you're doing here is you're filtering it out before you take samples so that it does not alias. Okay, there's your low-pass filter. Now, had you not, imagine you tried to do this backwards. You're like, well, I took samples at too low of a rate, but now I want to go remove the artifacts. Well, you actually can't. It's too late. They've been mixed in with your signal. Unless you know something about the signal, you won't be able to remove the artifacts. However, if you knew, for example, that the bandwidth, like in the picture I drew, was only a little bit above your signal, well, then you know, for example, that the aliasing that occurred, although it did mess up your signal, it only messed up a limited portion because the copies would only overlap here. So potentially, if you do know something about the bandwidth, you could actually filter afterwards to remove the aliasing, but what's going to happen is you have to filter out all of this stuff. So you lose more of your good signal. You'd have to apply a filter that cuts off at a lower frequency, okay, because you didn't do the anti-aliasing. All right, last thing I want to say, because it's relevant to your problem set, because you're doing a problem on sampling. So we have this vocabulary I'll introduce real quick. All right. There's a word called bandwidth. And usually that refers to this maximal frequency idea. Okay, and then people say the Nyquist rate is double that frequency, the sample rate you need. Now it's possible that there's actually an upper and lower bound on your spectrum instead of just an upper bound. And in that case, then you would say that the difference between the upper and lower bound, that's the bandwidth. Really, I don't test you on vocabulary, but it's good to know, what people are talking about when you hear these things. Another thing is, okay, but let me show that if you knew more generally about the spectrum, if you knew more generally about the spectrum, like, for example, you knew that, this is just an example, you knew it was between some lower and upper boundary. Okay. It's possible that you can sample in an unconventional way. This isn't the sampling theorem way of sampling. Here, the sampling theorem says you need 2 of f upper as your sample rate, right? But it turns out you can avoid aliasing. Like, for example, let's assume for the moment that fu is greater than that the lower boundary is greater than half of the upper boundary. So it's pretty narrow off to the side. Well, then I would argue that you could actually sample at only the sample rate equals fu and still avoid aliasing. Because if you look at what would happen, you would get, so let's now do our sampling at fu. So our delta train is like this. So we make copies, right? But as we make copies, when you copy this whole thing over to this delta impulse response to the right, you're going to get something like this. When you copy it over to the left, you'll get something like this. And if you keep copying, because you have, this impulse responses just keep going, right? You'll keep getting, it'll be periodic like this. And notice there's no overlap. So, it's the sampling theorem is a sufficient condition. But if you know more about the spectrum, it's possible you sample at a different rate and still avoid overlap. The reconstruction would have to be different. Sync interpolation would no longer be the way to reconstruct this, okay? Because sync interpolation would give you this thing, which is weird. But you could design a different filter. Notice all you have to do is design a filter. In this particular case, design a filter that just, filters out where just keeps where your original spectrum was. design that continuous time filter. That will be the new way of reconstructing for this specific setting. Okay, so you have a problem set where you do this very thing. We give you certain bands. You come up with the lowest sample rate that works. You just need to draw it out and figure out what's the lowest sample rate that avoids aliasing. And remember that the reconstruction now is different. It's not sync interpolation that works. Okay, thanks.
Let me continue with this lecture. I had more to say and the class time ran out. So back to this notion of bandwidth and Nyquist rate. Sometimes people refer to these by other names. For example, or I guess not by other names, but sometimes people just call basically the same name different things. So people might call the bandwidth actually 2 times the maximum frequency in some settings. Because if you look at positive and negative frequencies, then you get double from going to negative FM to positive FM. Or, to be even more confusing, they might say the Nyquist, rather than Nyquist rate, they might say Nyquist frequency is actually the highest frequency, so FM. So anyway, in other words, there are various settings in which these names might mean slightly different things. Okay. Now, I mentioned that you could do a non-standard sampling. If you knew something about the bandwidth that was unusual, something other than the highest frequency. In the case of this example, I said there's a highest and a lowest frequency. Then it may be possible to sample at a lower rate. Of course, with that would be the requirement that you reconstruct in a different way. You wouldn't be reconstructing with just sync interpolation. But we do have a notion of a lowest possible rate. It may not always be achievable, but let's assume that okay, let's suppose that the spectrum is like on certain sets of frequencies. So we have certain frequency ranges where we know the signal does not exist. It doesn't have a non-zero Fourier transform value. It might be something like this. I'll put 0 here, and then I'll arbitrarily make a spectrum here that we know is sort of contained in some sets of frequencies. Okay, if we know it's in those sets of frequencies, we can take advantage of that, of course, like we did above, to potentially, sample at some rate that doesn't have aliasing that might be lower than twice the highest frequency. But there's a notion of a Landau rate. If you take the sum of the interval widths, okay, then there's this so-called Landau rate, which is that sum. And this is a lower bound on the sample rate that you would need to avoid, to faithfully reconstruct. So if we look at the above 2 examples, well, if we go right up to the original sampling theorem, and we say, what would be the Landau rate? Oh, where is it? It's up here. Okay, if we have a highest frequency, FM, what is the Landau rate? Well, notice that all of the spectrum lives between negative FM and FM, so it's 2 FM. And we actually achieve that. The sampling theorem says you can sample at a rate of 2 FM and recover, or greater than 2 FM. So if we go to this other example, we said, well, sometimes you might have an upper and lower bound on your, you might have like an upper bound and a lower bound on the spectrum. So this blue was the original spectrum. Well, the Landau rate, again, would be twice the difference between these. But you can't just naively apply sampling theorem there. You can't just say, I'm going to do this bandwidth, which is actually the Landau rate, this lower bound. I'm going to sample there and then reconstruct. I And I'm not just saying you can't do it because you have to do a different reconstruction. Of course, whenever you do something other than the just an upper bound on the spectrum, then you have to do something other than sync interpolation to reconstruct. But you may not. There may be no good reconstruction because it depends on what's going to happen with the aliasing, and are they going to line up and hit each other or not hit each other. So this is a lower bound, but you can't just naively assume you can achieve it every time. Okay, I had two practical considerations, and I jumped into one of them here. All right, this anti-aliasing filter part. So let's go back here. I'd like to put some space. Okay, so I have some space now. So anti-aliasing was one consideration where, you know, in a practical setting, you want to get rid of the part of the spectrum that you aren't going to try to reconstruct because it could interfere with your reconstruction through aliasing. Now, the other thing is, in the reconstruction side, there's some considerations to make. We know that ideally, how are you going to reconstruct your signal? You take your sampled signal, xn, and you are going to do a low-pass filter. But first, we need to make this a time domain signal. So I'm going to call this, this is a continuous time process. It's going to produce impulse responses. Okay, because remember, I mean, we've been thinking of everything in the continuous time space, where we've been using impulse responses to represent our discrete time signal. So all I'm saying is this is just, let's say, some process that reads numbers from memory and produces, like, you know, delta functions of the appropriate heights in continuous time. Okay, then that gets fed into a low-pass filter. Continuous time low-pass filter. Notice that both on the sampling side and the reconstruction side, you do a continuous time low-pass filter. In fact, it's pretty cool that these are exactly opposites of each other. So out comes your x of t when you do that low-pass filter. Okay. Low-pass filter is going to be at cutoff of the sampling frequency over 2. Okay, so you see that they're backwards of each other, right? You do a low-pass filter for the anti-aliasing, and then you sample. Here you go back to continuous time and do a low-pass filter to reconstruct. Okay, so here are two things to consider about this process. All right, first of all, how do you do that first part? How do you actually take numbers out of memory, you know, this discrete time signal, and make a continuous time sequence of impulse responses? Well, impulse responses aren't very physically realizable. You can approximate them, make just very strong pulses with a certain amount of you know, like total impulse, which would be the integral of them. So very brief pulses, okay? But that's just an approximation, and maybe that's actually difficult to build in circuitry because you might have very large voltages or whatever's carrying the signal. Okay, so that's hard, but here's something very easy. We've already mentioned that it's easy to produce a zero-order hold. Okay, now, unfortunately, we don't really want the zero-order hold, so that would be something like this. These aren't supposed to be the same signal. I'm just drawing, you know. We've seen what it is before, so I'm not doing this very carefully. This just holds the value. Rather than making an impulse, as we were doing here, it holds the value until the next sample, and it holds that value. Okay, this is easy to actually build. So what's neat is we can actually use that in our reproduction without getting the wrong thing in the output. So let's look at an equivalent way of viewing this zero-order hold, or the zero-order hold. So xn comes in, and our zero order hold, I'm going to write a big box here, is actually, we can think of it as two parts. It would be equivalent if we did this in two parts, which we're not really going to do. We do our actual discrete time to continuous time process, this above thing that we said we can't do. Okay, imagine that we did it, and then we fed that into a convolution with a rect, right? We've already discussed that that's precisely what a zero order hold is. Okay, so our zero order hold, which we can build, can be thought of in two parts. We're not going to build it in two parts, but it can be thought of that way. Now here's what we actually want. Then let's just suppose before we were going to convert to continuous time and then do a low pass filter. Well, I'm going to say that we do a filter here, but I'm not going to say that it's a ideal low pass filter. I'm just going to say we do some sort of filter here. We're going to see that we want to actually modify this filter because we're using a zero order hold. Okay. So we notice that we have two convolutions in a row. So this is the combination of two convolutions is itself a convolution. Now we want this combination to be an ideal low pass filter. So if these combined were an ideal low pass filter, then great, we've done exactly what we set out to do, and we didn't actually have to build this process of making a continuous time delta functions. We just did a zero order hold. So how do we do such a thing? Let me insert a little more space here. Okay, so how do we do such a thing? Well, it's not too hard, because we just look at look at what the convolution with the rect is doing. We're kind of stuck with that, so let's just see what it's actually doing there. Convolution with rect. It's actually rect of t over sampling period. That's the particular rect that we would actually convolve with for the zero order hold. What is that doing? Well, in the frequency domain, it's rect is a sinc. Okay. Now this particular one, because of the time scaling, here, I'll draw a sinc. Actually, I want to redo that. I'm going to draw it really wide because it turns out it is wide with respect to what we care about. Okay. So the height ends up being Ts because of this time scaling property, and the width here, this is Fs, where it crosses 0, negative Fs. Now, what we wanted was an ideal low-pass filter with width Fs over 2. What we actually were shooting for was something like this. That's what we'd like the filter to be. And remember, that's the combination of these two filters here, these two convolutions. We want it to be like that. Okay, there's the ideal low-pass filter. So that's pretty simple. All we have to do is build, have the second filter be, you know, it's going to look like this, basically. It's going to be something like this. It's going to dip down like this to compensate for, oh, that's an okay drawing, but let me. There we go. So it's going to line up, right? It's going to be such that when you multiply this by the blue curve up here, the convolution with the rect, you actually get your ideal low-pass filter. So we could make the formula, and it's going to be the inverse of a sinc on this window, and then 0 everywhere else. Boom. So there we go. We avoided having to build this these impulse delta train type of thing. We can use our zero order hold and still get exact recovery. All right. Now, there's a second consideration here that I do need more space after all. And that is simply that we can't actually implement an ideal low-pass filter. Now, we talked when we introduced the ideal low-pass filter, we said, well, there's some issues with this. For one thing, it's non-causal, right? That may not matter. Being non-causal simply means that if you're trying to do this in a real-time process, you'd have to introduce a delay. So maybe that delay is okay, maybe it's not okay. Maybe a bigger issue is that the output depends on samples that are arbitrarily far away in time, because sync dies off. Not only does it depend on them, it depends pretty strongly. Sync dies off rather slowly. So this can mean that, for example, the edges of your signal, if you turn this thing on and off, it'll have a bunch of ringing. But I guess the last issue is that you actually have to build this in a circuit, and you have limitations on what you can do in circuits, okay? Because this has to be done in continuous time. All right, so anyway, for various reasons, we can't do a filter that's exactly like that. So instead what you get are approximate low-pass filters. You get things that are sort of like this. They die off, and if you, depending on how intricate of a circuit you make, you can have this be sharper. Okay, you can have it be very sharp. It just won't be straight down. Okay, so this steepness depends on, you know, the amount of circuit components you put in there and so forth. Now, one thing that you can do if you have trouble building a low-pass filter that cuts off very sharply, what you can do instead is sample at a rate that's high enough such that, because you'd have the same issue with the anti-aliasing filter as well. If you sample it right at the Nyquist rate, then you have to have a sharp cutoff, or you have to make sure that you're at least having near zero spectrum when you're, you know, in the region that would alias, so above the half the sampling rate. Okay, so that would mean you'd have to start losing content of the signal you actually care about, because you design this thing so that it's very low once it gets up to half the sample rate. All right, so you can get around that by just sampling at a much higher rate than you actually care about. Like for audio, we care about things up to 20 kilohertz. We have to sample at least 40, but notice CD audio isn't 40 kilohertz, it's a little bit higher. That gives you a little bit of room to you know, design an anti-aliasing filter that starts eliminating signal at roughly 20 kilohertz, and by the time it gets up to 22, it's eliminated almost everything. Okay, and the reconstruction side has helped just as much. That when you reconstruct, you know, you again have that little wiggle room because you increase the sample rate. Okay, now the last thing on the agenda is to discuss sampling in discrete time, which you call downsampling. So it's the same principle. So here we call this downsampling, and then the reconstruction you call upsampling. All right. So first of all, this is just like continuous time sampling. Not really much different here. So for example, you'll have something like, now you have a discrete time signal coming in, and you want to keep only, you know, every, let's say you downsample by a factor of 3. So you want to end up with something, exactly, you take only every third sample, for example. So now we have a discrete time discrete time impulse train. It's much easier to understand than the continuous time one. So let's say 3, for example, or n, that's the sample rate, ns. Okay. It's the same exact definition as the continuous time one, except that we're using Kronecker deltas instead of Dirac deltas, and that the period has to be an integer. Okay, so how it comes out, your sample thing. Now, there's one more step here. Notice if you do that, of course, you're going to end up, so here's some samples, some signal. Okay, and you keep every third one, let's say. So you eliminate the ones in between with your multiplication there. And you end up with, let me draw one more sample here. You end up with, zeros everywhere here. 0, 0, 0, 0. Well, the reason to downsample was so that you could get fewer samples. So then you remove the zeros. You convert this to actually a new discrete time signal. Remove zeros. Okay, in fact, I'm going to call this a new one, XS. Okay, now we've actually, in a problem set, looked at the consequence of removing zeros or adding zeros. I think we looked at adding zeros into a discrete time signal. We saw that it was extremely simple to see what happened when you added zeros in. So the process of going from the input to the output here was just a matter of stretching. It's the time scaling property for discrete time. So that's just ends up, removing zeros ends up stretching the spectrum. Okay, what we really care about is what happened from here to here. And it turns out that this property is going to hold. We haven't talked about the multiplication property for discrete time. There's a slight difference there. Convolution and frequency, but I have to introduce something called circular convolution, which will come in a later lecture. But this particular convolution is not that hard. So again, we're going to have the spectrum of the incoming signal, which is always periodic, right? So we start out with, because it's discrete time, we start out with something periodic. So usually we only plot it from -half to half because it repeats, right? So it has some spectrum. I'm going to just, to make it simple, draw it like this. Of course, it's periodic. Okay. So this is the discrete time spectrum. Now, when we do this multiplication, that impulse function, the Fourier transform of that, is also impulse train and frequency of 1/3, just like we'd expect. So it has one here, it has one at 1/3, it has one at 2/3, 1. Okay, so everything's exactly the same. And what you get are shifts, but because of the circular convolution, you only have to consider like shifting, the shifts that happen in one period. So in other words, you get a copy of your spectrum up here, centered at this guy. Oops, I'm not drawing that very well. And you get another copy, the third copy. It's going to be, let's see, what's a good color here? Gray. Something like this. Okay, so that becomes a spectrum. You add them all up. All right. Clearly, there's some aliasing here. So our discrete time signal, because we downsampled, we lost something, as you'd expect, and that comes in the form of aliasing. These things add up, just like we don't want if we want a faithful reconstruction. So just as before, we're going to, if the spectrum here was, the sample rate was, let's say, 3 in this example. So it's the sample frequency of 1/3. If the spectrum of xn was between -1/6 and +1/6, let's look at that case here. So suppose we knew that it satisfied the sampling theorem. So there's 1/6. There's 1, -1. So if the spectrum actually looked like this, and then it repeated, and then we did our delta functions. I won't draw those again. And then we looked at the copies that occurred because of this multiplication. We would get like that, get that, and there's no aliasing. Okay, now this last step of removing the zeros, all that does, like we said, it just stretches this spectrum so that the new, let's see, so this process here basically relabels the frequencies since we removed a factor of 3. There were 2 zeros between each sample. Then these get relabeled, so that becomes negative. That becomes a half. That becomes minus a half. This becomes 3. This becomes minus 3. And so basically we've renormalized, so now it's periodic with period 1 again. Okay, whereas as I drew it, it was period 1/3, but after removing the zeros, it's back to being period 1. Okay, it was already periodic with period 1, but the fundamental period was 1/3. Now it's back to 1. Okay, so that's downsampling. Upsampling does exactly the opposite, as you can imagine. You low pass filter first, and then you you low pass filter, and then you what you need to do first is just put zeros back in between your samples. So if you want to upsample by a factor of 3, you would put zeros between all of your samples, 2 between each one. Okay, that brings the spectrum back to looking like this. Then you do a low pass filter. Now, after you've already added those zeros in, you then do a low pass filter. Notice what that's going to do in a time domain. You put zeros in here, but then you low pass filter in such a way that you fill back in your samples that you had lost. Assuming that the spectrum was, assuming this was band limited appropriately, that you didn't lose information during the downsample, then you get it all back because you fill it back in with a low pass filter. Okay, usually you do lose content. So if this was sound, again, if you go back to lecture 3, you'll see me do an example where I use MATLAB's built-in resample function. They do all of this the anti-aliasing for you. So they do a low-pass filter first, then they downsample. Okay, that's the appropriate way to do it. And then if I go back and I upsample it, I'm going to get a signal that's back at the sample rate of my original, but it's going to have content lost because I had to lose content to do the anti-aliasing. So, you never, you can't just retain all of these high frequencies if you go to a low sample rate. Okay. Now, if you wanted to downsample to some new rate that was not an integer, I've kind of explained this as downsampling, that it requires you to do an integer downsampling. Okay, so you could go from, I don't know, you could, like our example, you could do a factor of 3 fewer samples. But what if you wanted to do a factor of 2.5 fewer samples? You wanted to take new samples that effectively are between the old samples. Okay, that can be done. The way it's done is you first upsample and then you downsample. So if it's any rational number, you can write it as a ratio, which will tell you what factor you should upsample first and then downsample to the new rate that you wanted. So there's one reason for upsampling. I sometimes get the question, why would you ever upsample in discrete time? You're not getting any new signal. You're just putting new samples in, right? And there's one reason. The upsample is a process of downsampling to some other rate. Another reason would be if you wanted to, going back to the reconstruction in continuous time, we said that if you that sometimes in order to ease the process of designing this low-pass filter, you might want to work with a higher sample rate. So what you would do is in discrete time, you'd get down to the sample rate of your actual signal, based on the bandwidth of your signal. So you can do all your discrete time processing with the lowest number of samples. You don't want to put extra sample rate. That's just going to burden your signal processing if it's not actually carrying extra information. But maybe as a last step, if you wanted in your reconstruction to reconstruct at a higher sample rate so that you can do an easier continuous time filter, then there's another reason to do upsampling.